QASS has intensively dealt with the topic of plastic injection molding in the last weeks and months. We have tried to apply the new toolkits, pattern recognition and adaptive programming to the challenges of plastic injection molding analysis. Here is a look at the new user interface with which we visualize directly on the machine which data we are recording, which errors we want to detect, and also communicate directly with the machines and the processes. Above right, pictures or animations of the plastic injection molding tools are placed. Structure-borne sound sensors are screwed to the outside of the mold, which scan all processes within the mold and can detect movement and ejector emissions up to the megahertz range. The picture directly below gives an idea of what the structure-borne noise emissions can look like. In the large image view, we can explain this in more detail. This shows the structure-borne sound emissions as recorded by our high-frequency microphones, with the volume over the time axis. In this case, we are dealing with 1.8 seconds, exactly the time in which this tool opens and ejects the components. We subject this data to a spectral analysis. We see 1.8 seconds again on the time axis. On the second axis, we read the frequency range, in this case up to 800 kHz. Vertically, the volume of the moving elements from the plastic injection mold. If we zoom in, we can see the details that appear in the tool every millisecond. Okay, back to the general view and back to the surface. Here, on the left side, the large graphic visualizes information about many microprocesses inside the tool. Listed vertically, we have displayed a time axis. The 1.8 seconds tool movement time, but now in milliseconds. Up to 1800 milliseconds, individual horizontal graphs are shown. The horizontal axis shows the process numbers. Each number an injection or ejection process. We look directly at the structure-borne noise emissions of micro movements in the tool over 10,000 tool cycles. Big data live. Okay, how do we even get to the estimate of these times? Let's take another look at the overview. We break the process down into distinguishable small units using data analysis toolkits. To do this, we use algorithms that make a statement about the volumes and volume changes inside the system. These algorithms, which we developed especially for the tool processes, determine distinguishable units of the movement of the tool, which we visualize here as small white boxes. This enables the software to detect and determine the various process cycles in the mold fully automatically. In this case, the software has identified 97 distinguishable sections, each of which represents the movement of individual slides or groups of slides or another operations inside the mold. Of course, we do not know from the outset what each individual movement means, but when anomalies occur, such as here at approximately 112,000, where we suddenly notice a jump point, the tool can of course be inspected and the errors assigned. So we reload the data that is generated shot by shot. To do this, I start a database query of the last 10,000 processes. I click on the vertical axis and scale the graphs, and we look at what happens in the process from about millisecond 600. In other words, we follow the emissions of a single concrete component in the machine at the red line here, just above 600 milliseconds. The next thing comes a few milliseconds later, this white line. As you can see, the standard deviation is significantly larger than the red one, which is smoother and it scatters even more strongly above 620 milliseconds. Maybe we scroll into the process axis. Here, clear outliers appear again and again in individual processes. The analysis can be done, but basically we are already conducting a statistical analysis of the data in the process and to alert when there is a significant change in these emissions. Okay, let's zoom out of the data again. We can see here very clearly the emissions of the tool over time. We can see several jump points on the individual elements of the tool that may have caused damage. On this basis, the mechanical wear processes of the tool could then be detected. The same mechanism can also be applied to the injection phase, to change inflow emissions or to the clogging of their ducts, which over time become dirty and then cause other noises in the mold. The concept is exactly the same. There are simply different frequency responses to be analyzed. QASS can provide a toolkit for structure-borne noise, a toolkit for injection molding systems, which can independently evaluate the structure-borne noise data during the movement of the machine, define and set thresholds, detect distinguishable sections, and from that moment on continuously monitor all these sections during production. Statistical methods are used to alarm significant deviations of the tool and machine condition. The system is capable of learning, can learn patterns, and continuously optimize them. This provides a fully automatic system for the detection of changes within the tool. The user interface surface is programmed as a modular system, so it is not fixed. If we need different requirements and different representations in a process, this can be implemented without any problems. Behind this interface is the complete acoustic analysis programming and machine learning toolkit from QASS. In the front end, there is a programmable interface that we can switch to edit mode, to rearrange the graphs, provide 2 or 3 of them, show animated images of the tool. Each of these surfaces can be saved and loaded to the gauge depending on the tool, so that the right view for the right tool can be provided fully automatically.